Have you ever noticed that if you start a new conversation with an artificial intelligence, it completely forgets what you talked about yesterday? Any new information you give it simply slips away the moment you close the window. This happens because of a phase called pre-training. Think of it like printing a massive encyclopedia. Once the ink dries, the knowledge inside is completely frozen in time. The machine can read from those pages, but it cannot write any new ones. Neuroscientists actually have a term for this when it happens in human beings: anterograde amnesia. It is a clinical condition where a person remembers their deep past perfectly, but they are entirely unable to form new long-term memories. Because modern computer models are built with this rigid architecture, they wake up every single day stuck in an endless loop. They experience the immediate present as if it were always brand new. This means that despite how clever these systems seem, they cannot naturally grow or adapt to a changing world on their own. To learn anything new, engineers have to take the system offline and manually force a massive, expensive update. Compare that frozen digital encyclopedia to your own mind. If you touch a hot stove, you instantly learn never to do it again. But if you decide to learn a new language, you gradually build that vocabulary over months of practice. Your memory functions as an active sorting process that's always running in the background, deciding which fleeting moments are worth keeping and which should be stored forever. The physicist Albert Einstein often pointed out that we cannot solve our problems using the exact same thinking we used to create them. To cure our computer models of their digital amnesia, researchers are looking directly at the biological mechanics of how the human brain actually learns. True continuous intelligence requires breaking away from a single static timeline. A system that can learn and grow needs to have its own internal rhythm. Your brain does not rely on a single centralized clock ticking at one speed. Instead, it coordinates activity through interlocking rhythms. Picture a one-man band where the musician plays multiple tempos all at the exact same time. Up top is a fast, frantic rhythm, the high-frequency gamma and beta brainwaves processing immediate sensory information rapidly. Down below is a slow, steady bass drum, the low-frequency delta and theta waves handling deep, long-term memory. Through a biological process called consolidation, your brain takes those fragile, fast-paced daily observations and slowly, steadily stamps them into permanent storage over time. If your mind did not play at these different speeds simultaneously, you would only ever react to what is right in front of you. You could never retain anything for the future. The most remarkable part of this biological rhythm is a trait called neuroplasticity. It means the brain has a uniform, reusable physical structure that can flexibly handle both fast sensory reflexes and slow memory building. This highlights a structural flaw in traditional computer learning. Correct designs force the entire network architecture to update its connections at the exact same speed, creating a massive bottleneck. This diagram shows nested learning. It organizes the architecture into decoupled levels, each with its own internal clock. Fast layers process fleeting sensory data, while stacked, slower layers simultaneously build permanent knowledge. By giving a digital network the uniform, reusable structure of a human brain, we allow computers to drum out multiple learning speeds simultaneously. Let's look at this diagram. On the left is the old way of AI, a flat, rigid pipeline with a single path for data. On the right is nested optimization. The system becomes a series of distinct optimization problems, each operating on its own timeline. Imagine this stacked structure. The top level acts as fast-twitch short-term memory, continuously capturing and compressing daily data. Beneath that, the bottom level acts as deep memory. It updates rarely, locking in only the most critical, persistent knowledge. By decentralizing the system's clock, nested learning allows a computer to safely separate the fleeting noise of a single day from lasting fundamental wisdom. The real-world payoff is that computer models can now learn new languages and complex tasks continuously, right on the fly, entirely avoiding the risk of erasing their previous knowledge. The hard barrier between a machine's initial training phase and its testing phase disappears. The model is simply always living and always learning from its environment. We have started building systems that actually grow, rhythmic networks that pulse with the same layered logic we find in our own heads. By moving away from frozen datasets and towards these rhythmic architectures, we finally give machines a way to live, learn, and remember alongside us.